So far in our discussion of carboxylic acids and their derivatives, we've established that carboxylic acids have a carbon double bonded to an oxygen, single bonded to an OH, and the OH crucially can act as a leaving group. So this is where carboxylic acids and their derivatives are different from aldehydes and ketones. Carboxylic acids and the derivatives have a leaving group attached to the carbon. Now that leaving group can change for the different derivatives. It could be a halogen in the case of acid halides. It could be an acetate group or a sort of carboxylate group in the case of anhydrides. It could be an alkoxide in the case of esters, or it could be an amine in the case of amides. But they're all different types of leaving groups. So if you're thinking about this generally, this whole chapter, you should think about carbon double bonded to oxygen, single bonded to a leaving group. That's the big picture. That's the conceptual picture here. Well, when you have a leaving group, that should remind you, that should suggest a type of reaction, in fact, the first type of reaction that you would have ever learned in organic chemistry, and that was a substitution reaction. In substitution reactions, you can have a nucleophile come in. A nucleophile can attack a carbon that has a leaving group on it, and that can kick a leaving group off, and that's a substitution reaction, because you end up substituting the nucleophile for the leaving group. Now the way you would have seen that in Organic Chemistry 1 would have just been having some sort of a carbon chain with a good leaving group on it. The leaving groups in Organic Chemistry 1 were often halogens. Because they're so big, they can handle having the electrons, taking electrons with them as they leave the molecule. They can stabilize the negative charge from those electrons by spreading them out over their huge space. So in Organic Chemistry 1, you would be, something that would look familiar from that would be having a leaving group on a regular carbon chain. And you'd have a nucleophile come in. The nucleophile would attack the carbon that has the leaving group on it and kick the leaving group off. And that was a regular substitution reaction. Now, you would have classified that, for example, as, you know, it's substitution, because what you end up doing here, what you end up changing, is having that same carbon chain, but having a nucleophile attached instead of the leaving group. So you replace or substitute the leaving group with a nucleophile. So that's a substitution. And the drive behind that, what drove that, was having this nucleophile attack. So it was called a nucleophilic substitution. And that was abbreviated in the names for different mechanisms. For example, you had an SN2 mechanism and an SN1 mechanism. And in both of those cases, they were substitution reactions that were instigated by a nucleophile. So they were nucleophilic substitution. Okay, so much for what you did in Organic Chemistry 1. We're really going to be doing a very similar thing about that, a very similar thing to that now, but instead of just having an alkyl group with a leaving group on it, like before, you're going to have an acyl group. And here you see the features that we've been seeing in this chapter so far, having a carbonyl carbon with a leaving group on it. Remember, if an alkyl group is just any carbon chain, it's usually represented just with an R, and an acyl group is any carbon chain, but where it attaches you have a carbonyl. So that would be something like this. We've seen that before. We've seen this distinction before in Friedel-Crafts. When you could do Friedel-Crafts alkylation, that was a way we learned how to put carbon chains on a benzene ring. So if you had a benzene ring and you want to make a new carbon-to-carbon bond to it, you could use some sort of an alkyl group, an R group, with a leaving group on it, a chlorine, and then AlCl3 as the catalyst, and that would put that carbon chain on the benzene. That was the Friedel-Crafts alkylation. An alkyl group is just any carbon chain. Also, we learned more specifically what a Friedel-Crafts acylation. That was if you had a benzene ring, you wanted to add not just any carbon chain on it, but a carbon chain that had a carbonyl. You'd use that acid chloride and then AlCl3, and that would put that carbon chain onto the benzene ring. But notice this double bond to the oxygen. That's there, that's the acyl group. And now in this chapter, so we've seen that acyl group before. That's an acyl group as opposed to an alkyl group, which doesn't have that carbonyl. So in this case, what we're going to end up doing in this chapter is we're going to have a nucleophile that comes in and replaces the leaving group. This is the overall picture. We'll draw the mechanism in just a second. The overall picture is you have the nucleophile replacing or substituting itself for the leaving group. So where the leaving group was, that's where the nucleophile goes. But in this case, it's not just an alkyl chain, it's an acyl chain. We have that double bond to the carbon, the double bond to the oxygen, so that carbonyl there. So this is still going to be nucleophilic substitution, just like in Organic Chemistry 1. But because we have that acyl group there, this becomes something a little bit unique. This will be nucleophilic acyl substitution. That's the official name for where you replace a leaving group on a carbonyl with a nucleophile. Now there's a general mechanism for this, 2 fundamental steps. The fundamental steps are the same fundamental steps as in the substitution reactions you learned in Organic Chemistry 1. The first one is nucleophilic attack. You need the nucleophile to come onto the molecule, and so you will always have nucleophilic attack. The second thing you need is for the leaving group to leave. So that was loss of a leaving group. Those 2 curved arrow patterns will still be there in nucleophilic acyl substitution. They're the 2 curved arrow patterns that will always be there. Okay, let's think just in a general way about how this reaction can happen. Let's say we have our carbonyl and it's bonded to a leaving group. And then we have some sort of a nucleophile. We know that the carbonyl carbon is slightly positive, so it's going to act as an electrophile. It's losing electron density to the oxygen, and in some cases it will also lose the electron density to the leaving group. Those things turn it into a good electrophile. The nucleophile will attack the electrophile, but the weakest bond is going to break. The weakest bond is the pi bond. Remember, you have 2 types of bonds. You could have a sigma bond. That's where you have uninterrupted overlap between 2 orbitals. So in the case of 2 s orbitals, you could see how those could overlap in an uninterrupted way. And that's a strong bond. You could technically make a sigma bond with any orbitals. Even with p orbitals, you just have to make sure that they overlap in such a way that you get uninterrupted overlap. That's the crucial thing about sigma bonds. On the other hand, you can get a different type of bond called a pi bond. That's where you have 2 parallel p orbitals. They can only be formed from 2 parallel p orbitals. And in this case, the 2 orbitals will overlap, but the overlap will be interrupted. This middle part where you have the node and the p orbitals, you don't have the overlap, so you don't have a bond, and so this pi bond is weaker than a sigma bond, which is strong. The first bond you ever form is a sigma bond. Every bond after that is a pi bond, and so we have a pi bond here going in the carbonyl, going to the oxygen. Well, since that's the weakest bond, when the nucleophile attacks, it is this bond that breaks. And that's where this nucleophilic acyl substitution is a little bit different from the regular substitution you saw in Organic Chemistry 1. Because in Organic Chemistry 1, when the nucleophile attacks, it was the bond to the leaving group that broke. Here, it's the pi bond that breaks. And so you form an intermediate. Now note that this first step we just drew is an essential step in all substitution reactions. It's nucleophilic attack. That will be present in every substitution reaction. The thing you want to put on the molecule has to attack in order for it to replace something else. So when the pi bond breaks, you end up with what is famously called a tetrahedral intermediate. the carbon that was in the carbonyl was sp2, and so trigonoplanar. Now it is tetrahedral. It doesn't have any pi bonds, so it's not using any of its p orbitals, so it can hybridize those to stabilize them, and so it becomes sp3 hybridized and therefore tetrahedral. So you get this tetrahedral intermediate. Now this oxygen here with the negative charge is sort of flapping around in the air. It's very reactive, and so it snaps back down. It feels a slight positive charge on this carbon here. This is slightly positive, first because it has a bond to the oxygen, which is electronegative, and often the nucleophile and the leaving group are also electronegative. So they all are stealing electron density from this carbon, which is slightly positive. The oxygen, carbonyl oxygen, snaps back down. Those electrons are attracted to that positive charge, creates another bond there, and that kicks the leaving group off. So here we have our second essential step in substitution reactions, loss of the leaving group. And after that happens, we have the final substitution product. We have the carbonyl again. We have a bond to the nucleophile next door, and the leaving group has left the molecule. So overall, this nucleophilic acyl substitution is very similar to the substitution reactions you would have seen in Organic Chemistry 1, except for this intermediate, this tetrahedral intermediate. When the nucleophile attacks, the pi bond breaks, the electrons go to the oxygen to give you an unstable tetrahedral intermediate. Those pi electrons on the oxygen snap back down and kick the leaving group off. So we started with the leaving group on our molecule, we've ended with a nucleophile. So we've substituted one thing for another, and we did that on an acyl chain, so nucleophilic acyl substitution. That's the overall mechanism for almost everything that happens in this chapter. The only difference is what the nucleophile is going to be and what the leaving group is going to be. Now, sometimes we may have to change the reactivity of the molecule. If we don't have a good nucleophile, then we have to turn this into an awesome electrophile, and so you can do a proton transfer to make that happen. Or if you have a nucleophile that's neutral, when it attaches it might have a charge, and you'll stabilize that charge with a proton transfer. In other words, if you think in a big picture, the mechanisms in this chapter will all be nucleophilic attack on the carbonyl carbon, followed by loss of a leaving group from the tetrahedral intermediate. And the only thing that we may have to add to that are proton transfers to either make molecules less stable or more stable. Remember, proton transfers means you're either adding an H plus on a molecule or taking an H plus off. Adding an H plus on can make something that's neutral unstable, or make something that with a negative charge stable. Taking an H plus off can either make something that has a positive charge stable, or take something that's neutral and make it unstable. So those proton transfers will affect the stability and the reactivity of molecules. And so we'll use those to do that in these reactions, these nucleophilic acyl substitution reactions, but the essential step for them is first nucleophilic attack and loss of a leaving group, the same as the substitution reactions you learned in Organic Chemistry 1. So in the next video, we're going to apply this general mechanism to some specific molecules and see how some proton transfers might be included.